Hi there, my name is Pedro Bertoletti and today I'm going to show you how I use the NuttX OS to monitor electrical energy generated by mini solar panels. First of all, let's consider the following problem to solve. In a certain place on Earth, there is an electronic device powered by one battery, and it uses solar energy to recharge it. This electronic device is located in a place where there aren't no internet connectivity. I mean, no Wi-Fi, no Ethernet, no such a thing. So, another way to upload data to the cloud must be used to get this monitoring data to the clouds for further analysis. Okay. As solar panels operation are crucial for the correct operation of these electronic devices, as it is one of the only power sources available to recharge this battery, it should be checked if the solar panels are working properly and generate enough electrical energy to recharge the battery. Use some kind of remote monitoring, as we can see, as we can see in the further slides. To solve this problem, this demo proposes a solution using NuttX OS and Sigfox LP1 connectivity. The solution consists of a Raspberry Pi Pico board running NuttX RTOS and a custom application, allowing periodic INA 219 chip reading to get and also accumulate the useful electrical energy generated exclusively for recharging the battery. Plus, from time to time, this application sends the total amount of electrical energy generated for battery recharge to a cloud system, to a cloud platform, making usage of Sigfox connectivity or Sigfox LP1 for this. The Sigfox transceiver used for this solution is a HT32SX from HT Micro manufacturer. It's a Brazilian manufacturer. ONS data, I mean total electrical energy measured so far, is received by Sigfox base stations. This data is forwarded to a Sigfox backend and finally forwarded through HTTPS through Toggle IoT platform, allowing data storage, visualization through dashboards, and also data processing as analytics and stuff like that. Note that Sigfox is a good LP1 connectivity for this. Once Sigfox transceiver power consumption is very low, it can run with only single battery, I mean an 18650 battery for years. And Sigfox transceiver can be miles away from a Sigfox base station. Getting deeper into solution schematics, as you can see in your screen right now, it contains three 12 volts mini solar panels in parallel. All the power generated by these mini solar panels are redirected through an LM2596 voltage regulator module, as you can see in the center of the screen, which drop the voltage level from 12 volts to 5 volts. This is done because the TP4056 battery recharge module, as you can see right to the LM2596, accepts 5 volts as input voltage to recharge battery. Finally, TP4056 takes action by safely recharging the battery. Okay. Note that only the useful energy generated for battery recharge step is monitored. I mean, only the useful energy is measured, what excludes power loss in voltage regulator and makes these measurements more accurate for its purposes. Now, let's take a look at this demo assembled. Okay. First of all, there is three mini solar panels, 12 volts, as you can see in the top of the image. So there's a development kit with an HT32SX and a Sigfox transceiver and I used this development kit just to get direct access to this Sigfox transceiver through Word and using AT commands, as we will see further in this presentation. Also, we used the Raspberry Pi Pico INA209 and mini solar panels circuitry, okay, to send the power generated by all these three mini solar panels to one single output. Also, we have a Li-ion battery. This battery model is 18650 3.7 volts nominal and single cell battery. Also, we have a voltage regulator LN2596 and a battery recharge module TP4056. In embedded software point of view, the solution comprises NuttX OS plus the application used for this monitoring. I mean, all this software is comprised or is present in just one binary, okay? Where the application takes the advantage from POSIX system calls and NuttX, Word, and INA209 drivers, standard drivers, to accomplish its goal. So this project, this solution takes advantage from what NuttX has to offer for a solution like that, and make the code more simple, more readable, and also more with a better quality, final quality. Okay. Therefore, NuttX is a great OS for this. Once it reduces software complexity, it makes everything POSIX standard. Also, the application runs in background through init script executed after the NuttX OS boots. This approach is way more interesting than use the application as an entry point for NuttX, as this is a very common solution for a project using NuttX OS. This is better because it runs in background and it clears the way to another applications, to another projects running in the same OS. So this approach allows future expansions for this project. Now it's coding time. I'm going to show you the application source code and detail how it works. Well, as you can see, the application code is located into apps, NuttX workspace, examples, and this Energia Solar INA209 folder. Okay, so it's built like an example, and it is not as an external app. So the code is put into apps, NuttX folder, examples, Energia Solar INA209. Here is the source code. Okay, it's very similar to the examples present in the apps NuttX repository, but I'm gonna show you how I got to the solution. Okay, so just to clarify, I'm using the INA209 chip. I'm getting these measurements, these readings through this device located at /dev/voltamp null, voltamp 0. Okay, so the INA209 is mapped into this virtual device. Also, I'm using the word to communicate to AT32SX through /dev/ttyx0, okay, device. And I'm using GPIO22 from Raspberry Pico board to reset the AT32XS module, okay. And also I'm sending the data from half an hour to half an hour, okay, what means 1800 seconds. This application makes use from these two configs. Okay, so it must be enabled into NuttX menu config. First is the floating point values can be written into a printf message, and the last one refers to wart 0 defined used in the code. Okay, these two are required to the application works. I'm gonna go to the main function, so I'm gonna detail each one as demanded. The first thing this application does is open communication with INA 219 device, okay, by opening it using read-write access. Okay, so if it fails, it goes to error handle routine and terminate this program. Getting further, I'm opening connection to WART1 to communicate to Sigfox transceiver, and here I'm using no block access. Okay, so if transceiver doesn't respond or doesn't send nothing to the NuttX OS or to the Raspberry Pi board, nothing happens, nothing's blocked. Okay, so if it opens successfully, okay. If not, handles the error and terminates this program. Very similar thing is done here with GPIO22, open as read and write access. The first thing after open communication to all peripherals is to make an initial read of voltage and current by INA 219. This is used because I need a reference, I need a starting value to the max voltage and max current thresholds, okay, the limits getting so far. Well, first thing to do with Sigfox transceiver is writing hardware resetting it. Okay, what is done with this routine, wait for any data reception, any data incoming from HT32SX, and send AT command to put this Sigfox transceiver into sleep mode. Okay, the working in sleep mode is very useful here once it is powered by a battery. So the more we can save battery, the better it is. Here I'm getting the timestamp or the time of the day in milliseconds, in seconds, sorry, and saving it into this variable. And we're gonna use this variable to control when I will send Sigfox data to guarantee it will send from 30 to 30 minutes. Into the main loop, it reads the INA 219, get the voltage and current values. Okay, voltage in volt unit, in current in the ampere unit, compares it to the previous max values. Okay, and also calculates the instant power from this measurement, and also accumulates the total energy in watt hour for this program. It prints these calculated and measured values and checks if it's time to send 80 commands through Sigfox transceiver with this accumulated electrical energy in watt hour. If it satisfies this condition, I mean, if it has it is half an hour after the last data sent, it sends data to the cloud. So as you can remember, we have put this HT32SX into deep sleep mode. Now it's time to wake it up and wait for some data to come from it. Okay, so we have to wait to the HT32SX send some data and reset this module, and here starts the Sigfox transceiver, how can I say, specific command for data transmission. First thing to do in this topic is send the Sigfox zone, Sigfox communication zone. I'm in Brazil, so the communication zone for Sigfox here is RCZ2. Okay, so I send a IT comment for this zone. Waits for some data comes from HT32SX Sigfox transceiver, and finally send the data. Compose the AT command to send the data through serial forward interface. Okay. Once this data is sent, Sigfox transceiver is put into deep sleep mode again to save power. I update the timestamp or the time, the temporization value in order to send the next package, Sigfox package, half an hour after this data sent, and also wait for 100 milliseconds to restart this whole cycle. Okay. As we can see here in the beginning, when some communication open fails, it goes through this label, erro execução. This label is here. It closes all the opened communications and return as -1, what indicates an error, an execution error. Okay, so the program is very simple. It just measures the voltage current. It make a backup from max current value in max voltage value. It measures the instant power. It also calculates or accumulates the energy in watt hour, and from half hour to half an hour send it through Sigfox connectivity. Okay, this software also makes use from this header file, which contains all the AT commands from this HT32SX Sigfox transceiver. Okay, so the code can be very clean, and the commands are defined here in this header file. Here's the cloud side of the solution. The cloud side of the solution is made by Tago.io IoT platform. The first thing when data comes from Sigfox backend to Tago.io platform is to be parsed, and this data comes through this payload parser. Payload parser is a piece of software that parser or extracts some information from the raw data, from the raw bytes sent by Sigfox backend here. All I do here is to parse the data, inform that I want a int 32 bits with big endianness starting at byte 0 divided by 10,000, as I multiplied by 10,000 when I sent it. So I get this value, store it into this temporary variable called energia watt hour, and finally I stored this value into a Tago.io variable, also called energia watt hour. Okay. Once I get this variable stored here in Tago.io bucket into Tago.io database, I can do whatever I want. Here I show a dashboard where we can see the total amount of electrical energy generated, the approximated localization of my device based on Sigfox signal, and also a chart showing the energy, the electrical energy generated in watt hour over time. Well, thank you very much for watching my presentation. Please feel free to contact me over LinkedIn and Instagram or my personal website if you want to discuss a little more about embedded systems, IoT, and technology. Bye.